In this lecture, we're going to summarize our lattice types that we have just derived with the T3 choices that we've made. And then we'll list um, the point groups, the three-dimensional point groups that are compatible with each lattice type. Here's a table that lists our systems that we've created: the triclinic, monoclinic, orthorhombic, tetragonal, hexagonal with the rhombohedral choice, and the cubic. And uh, in each case, you recall, like in the monoclinic case, remember how we had two choices. The side center and bodied center became the same, so there's kind of two lattices to choose from. In the orthorhombic case, remember we not only had three distinct ones where side-centered and bodied-centered were um, unique because there was no parallelogram base that you could shift like you could in the monoclinic case, and so therefore they're distinct. And then we picked up another one which is a face-centered, so quite a few varieties in the orthorhombic case. And then, of course, a bodied-centered and primitive choice in the tetragonal case, hexagonal, primitive, and um, rhombohedral, and then bodied centered and face centered and primitive in the cubic case. The point groups that can fit in here are fairly straightforward. In the triclinic case, we could put only one in one bar, and in the monoclinic case, we had shown that's actually how we generated it. We put in a twofold axis and showed that also if we had used a mirror plane, we get a monoclinic. And of course, we kept on going with that kind of, operation where we said, all right, now if I wanted to put in, say, three perpendicular twofold axes, I end up with a orthorhombic case, and so on. Uh, some of these are pretty obvious. If I'm going to choose a fourfold axis, then I better have a tetragonal where one of the the unique axis in tetragonal can be a fourfold. Sixfold fits into hexagonal, and so on. The cubic systems we already talked about with 2, 3, and 4, 3, 2 have the natural axial combinations that are compatible with thinking about the cube. The higher symmetries actually automatically fit in. And the way that you can sort of see that is you say, okay, we had done, like, for example, a twofold in the M. But the reason you don't have to think about 2 over M in a way is that what 2 over M does is induce an inversion center. And it should be possible to put in an inversion center in these lattices because of the lattice, the translational symmetry. And so therefore, in most of these cases, and in all these cases, the highest symmetry one, which we call the Laue group, which is the one with the inversion center, and it doesn't need to be considered separately because with a three-dimensional lattice and the insertion of, say, a 2, 2, 2, then by definition, we can put in an inversion center if we want, and it will be compatible because the lattice, the way that the T3 works, is that we will be able to put in an inversion center into the lattice point. It's a little confusing to think about it, but if you go back and review it, you'll see what I mean. The higher symmetry groups with the inversion center are called the Laue groups. So if you look through here, these are all the ones with the inversion centers. And the reason they're called Laue groups is that in the case of coming in from any direction and you flip the crystal around and then do X-ray diffraction from the other direction, you might have heard of something called the 180-degree ambiguity. So in a way, you can think about Laue, which is he's famous person for inventing the Laue pattern in X-ray diffraction. And so the Laue patterns and the X-ray diffraction look like, regardless, that there's a inversion center in place. And so you see these groups when you do X-ray diffraction from, let's say, a front side and a back side. So you would conclude that you have a inversion center. So that's why it's called the Laue group. But so just the fundamental part of that is just that, well, if I create a lattice with a twofold axes inserted and I want to make it compatible, I can certainly put in a mirror plane, because by definition, when I put the twofold axis in, right, I have a twofold axis coming out in some, structure like this, and it's coming out of this plane, coming towards me. And so then if I put in the plane a mirror plane, right, it just reflects everything down that's up. But of course, it's already the case because I have a lattice, right? And so I have these axes that go straight up and down indefinitely. And so it has to be there in effect. So of course, that means that when you think about this mirror plane and these axes, you get a inversions that are automatically induced. And so you kind of know that's compatible because, again, when I put in this twofold axis and it's coming straight out at me, then by definition, everything that's above this particular slice of the lattice I'm looking at also lies down below it. And so it will be compatible if I choose to put a inversion center in there. And so hopefully you can see from that little example with the twofold monoclinic case how that works. And so because you can generally think about the lower symmetry cases, you can whip through this actually pretty fast. In fact, you can see that by concentrating on the axial combinations, you can see very easily which ones have to be combined with which lattices. And the work of distributing 32 point groups is not that difficult. Of course, what is, if we now put these different ones into the lattice and look at all the variants that occur, there is, of course, 230 unique crystallographic space groups that are generated, and we are not going to go through all of them, but we'll go through some of them just so you can see how it works. And with the finishing part of this class in the crystallography, you should be able to, in the future, analyze or construct, if you had to, most of those things, both understanding symbols plus the symmetry rules and everything else that apply to the space group. So we'll end there and we'll start the next part where we will start to first of all show you the 230 space groups and work through what we're missing in order to understand what we might see in some of the 230 space groups, things like screw axis, which we haven't defined yet.